The ancient rocks of Mars contain carbonates that are chemical compounds formed in the presence of liquid water in far past. Minerals like siderite discovered at Jezero crater indicates that flowing rivers and lakes may have once existed on the Red Planet. Perseverance Rover utilizes instruments such as SHERLOC to analyze these Martian carbonates. SHERLOC employs a laser to excite molecules within the sample, energizing their electrons. This excitation causes the molecules to emit light at specific wavelength. By analyzing the emitted light spectrum, scientists can determine the mineral composition and isotopic ratios present in the samples with an accuracy of approximately 0.05%. Geochemistry allows us to interpret these carbonate structures. Different types of carbonates from under distinct environmental conditions, leaving unique isotopic fingerprints. For example, the ratio of carbon-12 to carbon-13 isotopes measured with accuracy of less than 1% can reveal the temperature and salinity of ancient Martian water. This sample exhibited a magnesium content 23.7% by weight compared to an average magnesium content of 15% in terrestrial carbonates. This difference suggests unique geological processes on early Mars, potentially linked to its mantle composition and distinct magma generation mechanisms. The search for signs of past life on Mars extends beyond carbonates. Astrobiology focuses on understanding the origins and evolution of life in the universe. On Earth, extremophiles demonstrate that life can persist even under harsh conditions like those found in hydrothermal vents. This knowledge informs our search for biosignatures, evidence of ancient Martian microbes within the rocks and soil analyzed by Perseverance Rover. For example, the rover has detected organic molecules like methane. These could be produced by biological processes. Determining the isotopic ratios of carbon in these molecules will further aid in distinguishing between biogenic and abiogenic origins. Specifically, the ratio greater than 1 indicates potential biological activity due to photosynthetic processes. Study of Martian carbonates provides insights into the planetary processes throughout the solar system. Water circulation patterns, volcanic activity, and atmospheric interactions are all reflected in these ancient formations. By comparing Martian carbonates with those found on Earth, we can refine our molecules of planetary evolution and understand how different factors influence carbonate formation rates and composition. For instance, a study published in Nature Geoscience journal showed that Martian carbonate formations occurred over periods spanning hundreds of millions of years, significantly longer than was previously estimated, approximately 10 million years for terrestrial carbonates. This suggests differences in tectonic activity and geological processes on early Mars. The rate of erosion on Mars is estimated at 3 meters per billion year, compared to Earth's average of 5 meters per billions of years, indicating a slower geological cycle on the Red Planet. Additionally, Martian carbonate crystals are often smaller than their terrestrial counterparts, potentially indicating faster precipitation rates in ancient Martian environments in far past. Average diameter of Martian carbonates analyzed by Perseverance is 10 micrometers, significantly smaller than the typical 30 micrometers size found in terrestrial carbonates. Evidence suggests that the possibility of trapped water beneath its surface. These subterranean reservoirs could potentially harbor remnants of ancient oceans containing up to 40% on Earth's known groundwater resources. The volume of these potential reserves is estimated at several trillion cubic kilometers, significantly impacting our understanding of Martian geology and its potential habitability in far past. These sources could possibly even contain fossilized traces of past life waiting to be discovered by future missions.